Okay, for part 2 of the JFETs lab, we're going to build ourselves a little amplifier. So what this amplifier is going to look like is we know that we have to supply a correct VGG and negative voltage on the gate just to turn the transistor on. So we're going to start with that. Okay, and we're going to leave this variable. We're going to vary it and then observe what it looks like. And then from there, we're going to go into a token sine wave. This is going to be 1 volt peak or 2 volts peak to peak at 1 kilohertz. A sine wave, it's just a token wave. It'll show up easily. From there, we're going to go into our transistor, drain, source, gate. There is a 4th pin on the transistor called the case, and we're just going to tie that down to the source. And then this is going to be connected to ground, and up here we're going to have RD. The job of RD is to convert ups and downs in drain current to ups and downs in voltage. And then the voltage is going to come out here. But the problem is that this voltage here is going to have some DC on it, and we don't want that. So what we're going to do is we're going to AC couple. We're going to run through a capacitor to a load tied to ground. And that means that whatever DC voltage we have here, that is going to be the center of the wave there, and it'll give us a nice wave centered at ground. So we're running a 10K resistor over here, brown, black, orange. We're also running a 10K resistor over here, brown, black, orange. We're putting in a 1 microfarad capacitor there. Now the capacitor may be polarized. It may have a plus and a minus side. They're not. Okay, so we don't have to worry about that. If you're doing this at home, however, and you're using your own capacitor and the capacitor is polarized, the plus side of the capacitor goes to whichever side has the higher DC level. So this is going to have a DC level of 0 to plus 10. This is going to have a DC level of 0. So the plus voltage, the higher voltage is going to be over here. And that, if you're using a polarized capacitor, that should be the plus side. Now for small voltages like this, it's probably not going to hurt if you connect the capacitor backwards, but it's a good habit to get into, to locate the node with the higher DC level and put the plus side of the capacitor on that level. So once we get this circuit built, pretty straightforward. And then what we're going to do is we're just going to turn on the signal generator, turn this on, and we're gradually going to just make this more and more negative, and we're going to start to watch a wave appear here. So when you set this up on your scope, we're going to have channel 1 be VS, 1, -1. And then channel 2, when we first start, the transistor is not really going to be turning on very much. It's going to look pretty unhappy. But as we bring the VGG into that sweet spot where this transistor likes it, what we should see is an amplified, inverted version of VS. And then as soon as VGG gets down to VP, the pinch-off voltage, this will start to clip and go away. So we're going to just measure this, try to get the largest wave you can out of this, and then we're going to do a calculation of what you expect to get for your gain for this. So to get, if you remember the formula for gain is equal to minus G sub M times RD parallel RL. That is the formula for gain for this circuit. We're going to show you how to get the G sub M of this transistor from the data sheet, which will be uploaded to Canvas. You'll be able to get to it yourself. You will also be able to get the VP on the data sheet, and you'll be able to compare the VP that you saw in part 1 with the VP spec and see if it meets spec. We'll show you how to get G sub M and see what kind of a gain we get here. And then the last part of the lab, we're going to ask you to just unplug the load resistor here, look at the AC waveform there, and tell me what you see there. Do you see any change in the AC waveform here? So that'll be the last part of the lab, and that'll give you something to write about in your discussions. So that is the AC part of lab number 4. Okay, welcome to part 2 of the lab. We have gotten rid of the DC measurements and we're just doing a transient now. So we are using our Instech GFG 8250A signal generator, number 553, and we're using our Tektronix MSO 2012, number 650. So what we're going to do is we're going to now use this for the AC plus the DC offset feature for the DC. So we'll be able to pull this knob out like so, and we can dial in DC offset as much as we need. So this is going to be our AC and our DC power supply. And then on the oscilloscope, we're going to set up channel 1 to measure the source voltage, and we're going to set up channel 2 to measure the output voltage. So we've just got to modify our circuit a little bit. We're now going to run our signal generator here on the negative side to ground. Let's clean up this wire. We don't need it anymore. We're going to run our negative side here to ground and the positive side to where the VGG came in before. Okay, so that was this lead here, which we're not using anymore. And so the positive side is going to get, if I can horse the clip under there, we got it. Okay, and I've turned the amplitude all the way down. And now we just need our scope. So channel 1 is always the yellow channel. We're going to connect that to our signal generator itself. And again, I like to connect that here on the outside so we're not tugging on any circuit components that are plugged in. And then let us connect our ground lead to the ground lead there on the board, like so. So here's channel 1 directly on our signal generator, and this is a good time to set the signal. So channel 1, and we got nothing. So let's turn the amplitude up. And I don't like to use the auto set, but let's use it for now. Okay, looks like we have ourselves a triangle wave. So we're going to switch to a sine wave. However, we will be going back to a triangle wave later. And you're supposed to set this to 1 volt peak to peak. So right now our vertical scale is 2 per division. Let's set that to 1 per division. And we'd like to get a wave that's peak to peak plus or minus 1 division. So we're going to turn our amplitude down, like so. Now that is 1 volt peak, 2 volts peak to peak. And then our frequency, we're going to dial up 1 kilohertz, which is right about there. So now that that waveform is set, I'd like to slide it to the top of the display. Okay, thank you. I'd like to move this up and make lots of room to display channel 2. So channel 2 is going to be the blue channel. I don't think we need the cursors. So now we have channel 2. Let's turn that on. And let's just confirm that it works. Let's just double up on channel 1, see if we get the same waveform. But at least make sure we're in the same ballpark. Looks good. So channel 2 is set up on 1 volt per division. Let's slide it down a little bit also to make a little room. And we can shut the menu off. So now we are ready to bring our amplifier alive. So what we're going to do is we're going to set the VDD to 12 volts. VDD, if you remember, was V1 here. So we're going to set this to 12. Okay, that is our VDD. And now we can, with this node, we're going to take a look on the drain, and we have to AC couple. So we're going to connect the capacitor from the drain off to another node over there, and then another 1K load resistor from that node to the ground bus, which we could also just tap into right here. Okay. So now we have, coming off the drain, we're going through our 1 microfarad capacitor, and from there through the 1K resistor, and then from there to ground where we have the source in case grounded. So we can now connect up our probe here on V out. I'm going to clip it onto the resistor. It just tends to be a little heavier wire. And what we see is we kind of have some amplification, some response. We notice that the wave is out of phase. It's inverted, which is good. So we know the amplifier is working in some way. So what I'd like to do now is I'd like to apply some offset. And we have an amplification of roughly 1, but the waveform is distorted, so it won't be a very reliable meeting. Yep. But as we apply some offset, what we should see is a range of voltages that it works over. And so we have kind of a sweet spot here where the input voltage is at about the right range. And to notice the offset on channel 1, let's set channel 1 to DC coupling. So the vertical menu, channel 1, coupling. Oh, it's on DC already. Okay, good. So what we'll notice is we change the offset, the wave moves up and down. When the wave is entirely positive, that is not good. The transistor is unhappy because we're now forward biasing those diodes on the gate. And when we bring it negative, it works a little better until we get to VP, until the pinch-off voltage. Let's get that to hold still. And now as soon as we get down to the pinch-off voltage down here at -5, we notice the transistor is shut off and the waveform is clipped. So it looks like the best we can get out of this circuit is about that. Let's set the trigger level a little bit.
Set to AC triggering.
Oh, okay.
Trigger menu.
Okay, let's do the trigger menu and trigger
Coupling.
AC. Let's see. Coupling. Let's do a high frequency reject. I assume that's AC.
Yeah.
Okay.
And then hit the menu off again.
Okay.
Yeah, that should stay triggering.
All right.
Yeah.
So what we see is down here when we're below pinch-off voltage, the transistor is dead. V out is at 0. And we find that kind of sweet spot, that range that it works by. Not that one. Where it seems to work the best is right around in there. So let's make a note of our gain. It looks like we have a gain of about 1. It looks like the output voltage and input voltage are about the same amplitude, but you'll notice that as we bring the offset positive, it starts to lose it. Still. Yeah. But we can see that the output voltage is a little bit changed, but this is about the sweet spot where the transistor seems to work the best. So that's about the biggest wave that we can make. And it looks like we have a gain of about 1, just a little bit more than 1. It looks like the blue wave compared to the yellow wave is just slightly bigger. The blue wave is about 2.6 divisions, and it's about a gain of 1. So here we see our first amplifier. Now, just to show you what's on the other side of the capacitor to illustrate the DC coupling, channel 2 you see is centered at ground. But if we were to look on the other side of the capacitor, on the drain itself, we see channel 2 is centered way up here at around 7 or 8 volts. And the thing is, you do not want to send that DC to the load. You only want to send AC to the load. So what the capacitor gives us is the same waveform. Let's just slide it down a little bit. Same waveform, but a different DC level. But a different DC level. I unplugged our ground here for a second. But a different DC level. And that's the job of the capacitor, and that's what AC coupling is. Same waveform, different DC level. So it looks like we have a gain of 1. And then the final question in the lab is, what would happen if you temporarily unplugged the load resistor? So let's just for fun, let's yank the load resistor out and see what happens to the output. And what we see is that we get basically a doubling of the output waveform. So the formula that I gave you for voltage gain, where it's RD parallel RL, if RD is equal to RL, they're both 1K resistors, unplugging that is going to double the gain, and we're seeing about twice the gain here. The waveform is now 1, 2, 3, about 4.2 divisions, when before, under load, it was at around 2.2 divisions. So we've seen a roughly doubling of the gain. Now to look at nonlinearity, we can flick this to a triangle wave. So we have a nice linear triangle wave coming in, but you notice the triangle wave coming out has some distortion to it. That's something we talked about in lecture, is that different parts of the curve to give you different gains. And what we're seeing is that distortion of the wave in that nonlinear part of the curve. And so that's what we're seeing here. Actually, if I was smart, I would just trigger on channel 2 because that's AC coupled. Source. Trigger menu. source. Okay. So now you can see the nonlinearity in this wave when you're out of that sweet spot where the input voltage is correct. And then even here, you can see some nonlinearity in this wave. This doesn't show up very well in a sine wave, but on this triangle wave, it pops out. It's very easy to recognize nonlinearity distortions in the wave with this. So this should take you through everything we need to do for Lab 4. Some of you will be in class doing this with me, and some of you will be staying home doing this vicariously. And it's up to you, but this lab will be released on Friday. Okay.